Recall that in an E2 process, you have the proton transfer, the base steals that beta hydrogen, the electrons go toward the leaving group, so that's proton transfer, and you have loss of a leaving group happening at the same time. And so two molecules are really involved in that. You have the substrate, and you have the base. Both of those molecules influence how fast an E2 reaction happens. So if you're trying to think about it in terms of equations, to translate that thought into math, the rate depends on the units you use, and so that little k is just a conversion factor to take into account units. But it depends on both the substrate, that's in blue, and the base, that's in orange. So the rate depends on two things, and notice one of those things is the base. Now, if you compare that with an E1 reaction, in an E1 reaction, you still have those two steps, but they happen one at a time. And the one that happens first is the loss of a leaving group. And that takes time, because that molecule, the substrate to begin with, is pretty stable. It has to get it has to get slapped in the face really hard in order to kick that leaving group off. So that's really stable, whereas once you form the carbocation, that molecule is now much more energetic, and so it doesn't take as much energy, and so it doesn't take as much time for the base to steal the beta hydrogen and to form that pi bond. So the rate limiting step here in an E1 reaction is this first step. It would be as if that first step takes 15 minutes and the second step takes like 100 trillionths of a second, just to conceptualize the difference. The rate is really determined by that first step. And so, notice the only thing involved in that first step is the substrate. The base is not involved in that at all. If you add more base, it would speed up the second step. So instead of 100 trillionths of a second, it might be 10 trillionths of a second. But you'll still have to wait that full 15 minutes for the first step. And so the rate overall is really the same. Effectively the same. It's defined by that first rate limiting step. And so if you're trying to think about that discussion translated into an equation, you'd say, okay, how fast the reaction goes depends on the units, so I'll have that conversion factor, that little k there, but really it's just going to depend on the substrate, because the rate limiting step only has the substrate in it. So only the substrate's there. The base shows up in the fast step, not in the rate limiting step. So concentration of base won't speed up an E1 reaction. And this is why we saw in the mechanisms that we drew that an E2 reaction often had a strong base. A strong base speeds up the E2 reaction. And if these two are trying to compete with each other, a strong base will speed up the E2 reaction, it won't do anything for the E1, and E2 will win overall. Whereas an E1 reaction often used a weak base. Because if you have a weak base, that slows down the E2 reaction, and so the E1 outcompetes it. Okay, well, let's use these rate laws now. Now, in exercise 813, it gives you a reaction, and they give you a crucial piece of information here. They say that it's second order. It's second order, that means it's E2. The 2 there is referring to the fact that it's second order. The rate depends on two things, the substrate and the base. So the rate law that we're going to be using is going to be the E2 rate law in each of these questions. For this exercise. Okay, so they're going to ask how the rate of the reaction changes when you change the concentrations of things. Well, now that we know the rate law, we just have to plug in a few numbers. You always want your reference point to be 1. So what if everything were 1? Well, okay, fine. 1 for the substrate, 1 for the base, that's 1 for the rate. Now we can think about what happens if you double or triple the concentration of the substrate or base. What happens to the rate? Well, in this case, it says what happens to the rate for A? What happens to the rate if the concentration of chlorocyclopentane, now that is our substrate, that has the leaving group on it, is tripled? So we're tripling that. And the concentration of sodium hydroxide is our our base, what if sodium hydroxide remains the same? Well, then it would stay as 1. Now remember, these are being multiplied, so really the rate would increase by a factor of 3. The rate would be 3 times faster. And knowing how the rate changes when you change the concentrations is really useful, because this is something you can do in a laboratory. You can easily change the concentrations of the substrate and the base in your beaker, and you can measure how fast it takes for the reaction to happen. So you can see if you do get this result, and if the base ends up changing the rate, then you know you have an E2 mechanism. But if it doesn't, then you know you have an E1 mechanism. And since those give you different products, you can use that information to predict what product you're getting. So this is a useful exercise because it's something that's easy to measure in a laboratory, and that gives you a lot of information about what's happening on a molecular level. Okay, so that's that one. The rate would go 3 times faster. How about in B? It says, what happens to the rate if the concentration of chlorocyclopentane, that's our substrate, remains the same? Okay, so we're comparing everything to 1. So what if that remains the same, and the concentration of the base, sodium hydroxide, is doubled? In that case, 1 times 2, the rate would double. And then for C, it says, and we're going to compare everything to 1, so what happens to the rate if the concentration of chlorocyclopentane, that was our substrate, is doubled, and the concentration of sodium hydroxide is tripled? Now remember, you multiply these, that means the rate would go 6 times faster. Oops. Okay, so that's how you can sort of think clearly through how concentration affects the rate for an E2 reaction. Now let's think about an E1 reaction. In 826, they say the following reaction occurs via an E1 mechanism, and they give us our reaction. Notice the thing with the leaving group is the substrate, and the base here is a weak base. It's ethanol, which we talked about in one of the videos on E1 mechanisms, ethanol, drinking alcohol. So in this case, it's an E1 reaction. They tell us in the prompt, and so we're going to use the rate law for an E1 reaction. That only depends on the substrate. So we'll use that in each of these exercises. So in this first one, it says, and we're going to compare this to if everything is 1. Okay, so it says, what happens to the rate if the concentration of tert butyl iodide, that is our substrate, is doubled, and the concentration of ethanol, that's our base, is tripled? Well, the base doesn't show up in the rate law. The base doesn't speed up the rate limiting step of an E1 reaction. So that's not going to speed up the reaction at all, and the rate will just depend on the concentration of tert butyl iodide, the substrate. So the rate would double. So notice in an E1 reaction, the base does not affect the rate. And with B, it says, what would happen to the rate of the concentration of tert butyl iodide, that is our substrate, remains the same, and the concentration of ethanol, our base, is doubled? Well, again, the base doesn't show up in the rate law, and so the rate only depends on the substrate, and so the rate here would stay the same. So hopefully this gives you a sense of how you can think clearly and methodically through how the rate of an E2 and an E1 reaction would change when you change the concentrations of the substrate and the base.